Fakulti of Earth Science have been established in 2012. We are in one of the youngest university in Malaysia. We have a vision to become a pioneer in sustainability, environment, and natural resource through entrepreneurship agenda.
Currently, Faculty of Earth Science offering 3 undergraduate programs. We also have 2 preparatory programs which managed at Faculty of Earth Science.
For Bachelor of Applied Science, Natural Resource with Honours, the focus of this program are much more on our biosphere, which means we are focusing on our plants, our animal, and also the management of our tropical forest. For another program, which is Bachelor of Applied Science, Sustainable Science with Honours, the program itself relate more on environmental element, which is we would like to sustain our environment together with the importance of economy and also social.
Always apply teaching and learning session by using technology such as by using GIS, drone, geospatial mapping technology, and also modeling. Students also be taught with to integrate geoscience understanding from classroom or practical learning with geoscience data from a variety of sources, creatively using the latest digital technology.
Science Preparatory Department is a new department and need to taking care and manage of 2 academic programs. Both of these programs will need to learn biology, mathematics, chemistry, and also physics.
Faculty of Earth Science Museum, actually we have various dry and wet specimens such as insects, small mammals, reptiles. Besides that, we also have rocks, minerals, and also fossils. So actually all those specimens being collected by our students.
To stay relevant, we have to be flexible. Besides flexible, we have to be unique. In Faculty of Earth Science, we have multidisciplinary research. Recently, we are focusing on the research on minerals and the fossil. Other than that, we use remote sensing and GIS in monitoring forests and urban planning. This research has been successfully done within our capacity of staff, supported with the grant that we received from government and other agencies.
We are optimistic to become one of the best faculty that focus on in environmental in Malaysia.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good evening to all of you. I am Dr. Mohammad Khan, the moderator of this webinar. Firstly, we like to apologize for 30 minutes delay due to some technical issues. The Faculty of Earth Science, Universiti Malaysia, Kelantan, organizing an international webinar series 3 on clouds, contrails, and climate change, emerging aviation technologies to reduce climate impacts. So in today's webinar, we have 2 experts. This expert will be deliver their speech and sharing on these topics. So the first our panel is Dr. Marieanne, and the second panel is Dr. Sara Qureshi. So I would like to remind you, all the audience and viewer, please register this conference. The link will be sent during the talk, and after register, the audience or viewers will get an e-certificate. So I would like to invite our first speaker, Dr. Marieanne. Dr. Marieanne is expertise of atmospheric thermodynamics, cloud microphysics, climate change impact, and natural resource management. She is a senior lecturer in the Faculty of Earth Science, Universiti Malaysia, Kelantan. The title of Dr. Marieanne is Responses of Clouds to Climatically Perturbed Thermodynamics Environments. Okay, one more request before we start. Please, if you have any question, comment, or suggestion, please write in the chat box of the FB or in the comment box. And please mention your name, and also please mention the question or the comment refer to the speakers. So now I'd like to invite Dr. Marieanne. So the floor is yours, Dr. Marieanne.
Thank you, Dr. Muqtada. So can you see my screen? Or are you able to see my screen now? Okay, yes. All right, so I'm going to put this on presentation mode. All right, so hello everyone. Good afternoon or good morning to all of you, and thank you so much for attending this webinar. So, and thank you also to Dr. Muqtada for the introduction, and to Universiti Malaysia Kelantan for organizing this webinar. I'm excited to be here to share about my work and also to learn about new emerging technologies, aviation technologies, to reduce climate impacts from our invited speaker here, Dr. Sara Qureshi. So I go by my friendly name May, and I am here to tell you stories about clouds. And essentially, well, I'm going to make this very simple because so as to cater to a wider audience, because I think not everyone here is familiar with the science of clouds and climate, and it can get pretty complex. So I try to make it very simple but interesting. So hopefully by the end of this webinar, your appreciation for clouds and climate will grow, and perhaps we can even collaborate on future work. Okay, so I'd also like to mention that it may get a bit technical when we come to the research part, so please do bear with me. All right, so here's my title. We'll explore the range of responses of clouds to climatically perturbed thermodynamic environments. So in other words, we are trying to see how clouds react or respond to different climate change scenarios. So this was part of my PhD work, and that is why I included my supervisor's name, Stephen Dobby, from University of Leeds. I'd also like to briefly mention my collaborators who have helped me a lot in this work, which is Professor Sonia Lasher-Trapp from the University of Illinois, and Cecile, who is now a meteorologist at the US National Weather Services Department. Right, so let's start with the big picture. Why are clouds important? Well, for obvious reason, they give us rain. And secondly, whether you realize it or not, they actually help to regulate the Earth's temperature. So depending on the type of clouds, they either warm or cools the Earth. Okay, so now how do clouds do that? Well, first of all, they do that by transporting water or moisture and heat from the ground up. Okay, so I'm sure we're familiar with this, the biosphere. And water is everywhere. It's in the soil, on the tree, in the trees, oceans, drains, you name it. Okay, so what happens when sun rises? So what happens is that when the sun heats up the surfaces, okay, the surfaces gets warm, and then water will then start to evaporate. So when they start to evaporate, they will then, as they travel up the atmosphere, you know, as we go up the atmosphere, it gets colder, at least in the troposphere. So when it gets colder, this water vapor will condense back into liquid water, okay? And that is how clouds are formed, all right, through condensation, okay? Now, besides besides transporting moisture and heat from the ground up, clouds actually also distribute heat and moisture horizontally across the globe. Okay, so from equator to the poles. So how do they do that? So we have our Earth here, and we know that the equator is hot because we receive the most direct and concentrated sun rays. Whereas in the poles, the sun rays hit at a slanted angle, so it covers a wider area. So the area is heated less. All right. Sorry. So that's why the equator is hot. And not only that it's hot, it is also humid. So we get clouds. So we get clouds, okay? As the surface is warmed up, the air rises. And as it rises, it cools and forms clouds. And, you know, clouds, when it reaches up to the atmosphere, it doesn't just immediately disappear into space. No, it is constrained by our first layer of atmosphere, which is the troposphere. So once it reaches the top of the troposphere, most of the time, it cannot penetrate into the second layer of the atmosphere. Okay, so what does it do when it can't go up? It will then go sideways. Okay, so it will try to go poleward. But it doesn't go all the way to the poles due to some pressure differences in certain locations. So in this case, it will stop at 30-degree latitude, okay? And then the air will all come down, all right? Now, once that air comes down to the Earth, it hits the surface, it then would want to distribute sideways. So it will go sideways again. Now, this air will then continue its journey to the poles. However, at 60-degree latitude, it will encounter a different kind of environment. And that environment is very, very favorable for cloud formation. So then air will rise up again and form clouds. Now, I think you get the gist here. So once it reaches the troposphere, it will then distribute the heat and water back until it makes its way to the poles. Okay, so once it reaches the poles, the air has nowhere else to go, so it has to come back down to Earth. So when it comes down to Earth, it again distributes the air. So what happens on this side of the Earth will also happen on the other side of the Earth. So this is essentially how clouds move around heat and moisture, both vertically and horizontally across the globes. So this is why clouds are very important. Okay, so now that we know the important roles that the clouds play, let's look at what are needed for clouds to form. So here's the recipe for cloud formation. We need 3 main ingredients. Firstly, moisture, where we can get from plants, soil, or ocean. And secondly, we need heat to provide buoyancy for the air parcel from the ground to go up to the atmosphere. Okay, and last but not least, one that many might be unaware of is that we need aerosol. So what are aerosols? Aerosols are tiny airborne particles that stay suspended in the air. So like dust, smoke, sea salt, pollen, and even virus particles. So that is why coronavirus is very dangerous, okay, because it's airborne. Now, what this aerosol do is that it provides a surface where water vapor can condense onto. Okay, so it will attract water vapor into it in order for condensation to happen. So if you imagine at the bottom here, you see a waves of clouds. Now imagine that waves of clouds to be waves in the ocean. Okay, so we get our source of water from the ocean, represented by the blue dot, and then the red dot, let's call it dust. Okay, so when these two mingle together in the atmosphere, they will start to be attracted to the dust. Okay, the water molecules will condense on the dust. Okay, and then when more water molecules condense on the dust will then be engulfed by these water molecules. So in reality, if you look at a microscopic sample of air, it would look something like this. Okay, so when more of this water vapor has condensed onto dust, then we get clouds. All right, so that is how clouds are formed. Now, any changes to any of these ingredients will definitely change how clouds form and evolve. In this work, I focus on moisture and heat. I modify the profiles of moisture in terms of humidity and the heat in terms of potential temperature. Here I represent it by the Greek letter theta. So in the rest of this talk I will mention theta instead of potential temperature. Okay. Now the underlying physics behind the balance between heat and moisture is the Clausius-Clapeyron equation, which states that as temperature rises, evaporation rate is faster. So we get more water vapor in a hotter climate. Okay. However, many studies have found deviations, both left and right, from this equation. So some areas they found the rate to be doubled, while in some areas they find the rate to be less than what is expected. So, of course, this is because there are many things that can influence the balance between heat and moisture. And one of them is the vertical structure of heat and moisture itself. And that is what I am isolating in this work. Okay, and so yes, that's all. That I will explain more in detail how I did it. But first, let me introduce the cloud of this study. So the cloud that I study is the deep convective cloud, or in general, we call them thunderstorm. Now, I'm not sure if you know this or not, but our rain is actually formed by two processes, either warm rain process, which occurs in the lower part of the cloud, or by the ice processes, which occurs in the upper part of the clouds. Okay. Now, traditionally, the deep convective cloud or thunderstorm, the rain formation in this cloud is mainly dominated by the ice processes. But as climate continues to warm, researchers have found warm rain process to be more dominant in producing rain. That is why we get very intense rain at a very short time duration. So it's because of this, right? And I'd also like to share the top part of a deep convective cloud, which is called the anvil, that I spotted in York when I was studying in the UK in 2016. So this is just for sharing, right? Right, now that I've given you a little bit of introduction, let's travel to my study area, okay? So my study area is in the US, and we are now in Malaysia, Pakistan, and maybe some of you in the UK. So let's all travel to the US and parachute down. And here we are, we have landed in these 8 locations spread over the Midwest and the southeastern part of the US. So in the Midwest, you see that we get our source of moisture from the Great Lakes here. Whereas in the southern part, we get our source of moisture from the Atlantic Ocean and the Gulf of Mexico. All right, I'm sorry if I'm being too fast here. I try to slow down from now onwards because it's going to get a little bit technical. Okay, so the methodology that I use is the modeling approach. So what I do is that I get climate data, I modify them, and then I put them into a cloud resolving model. So the climate data that I use is the US CCSM3 Global Climate Model. It is prepared by Trepp et al. And given to me by Cecile Villanueva Biriel, my collaborator. The climate data is a 30-year average of the past and future simulations at locations where the average CAPE is over 1,000 joules per kilogram over the summer months. So CAPE here is actually an indicator of how likely convective activity is going to happen. So the larger the number, the greater is the possibility for convection to happen. Now, as with all climate data, they all have biases. So Cecile has corrected these climate biases using 2 reanalysis data from the NCEP and NARR. So once I get these profiles from Cecile, I modify them in terms of the vertical structure of potential temperature and the relative humidity, and I also add or remove warming to these profiles. Okay, I'll show you the experimental design afterwards. Now, once I've modified these profiles, I then plug them into this cloud resolving model called WRF. It's developed by the US, called Weather Research Forecasting, and it's version 3.8.1. And what I'd like to highlight here, since it is a cloud study, the microphysics scheme I used is the Morrison two-moment scheme. But instead of using the default version, I actually used a modified version that I obtained from Beth and White in Oxford Uni, because it includes double moment for the cloud water, whereas the default does not include double moment for the cloud water, which is essential, especially in this study. Okay, so here are my experimental designs. So I have 4 experiments. 3 of them are non-warming scenarios, and then 1 of them is a warming scenario. So in all of these experiments, I change the future environment, and then I compare for the non-warming to the past environment. And then for the 4th experiment, I actually compare it to the original future environment, okay, because I removed the warming. So what did I change? So in the first experiment, I changed both the vertical structure of theta and relative humidity. And then in the second experiment, I changed only the vertical structure of theta. In the third experiment, I changed only the vertical structure of relative humidity. Okay. Now in the 4th experiment, I just removed the warming. Okay. Now experiment 4 is the odd one out. It should actually look like this. Okay, I should actually modify the past and add warming, retain structure, and compare it to the past. But I only realized it after my PhD, and I actually also did a simulation on this and found them to have similar results. So because I do not at this moment have access to my latest simulation, I will show you the old results. So apologies for that. Now, what are we going to track in all of these experiments? So we will see how the thermodynamic environment changes when we modify the profiles. And then in that environment, we will see how is the physical structure of clouds changing also. Okay, so that would be in terms of the cloud base height, okay, or lifted condensation level. And then the freezing level, where it is 0 degrees Celsius in the atmosphere, and then the cloud top height, and then the warm phase cloud layer, so that we can know how active or less active the warm rain process is, and then the cold phase cloud layer, so we can know whether, you know, how active or less active the ice processes are. Once we see this, we will then zoom in to the cloud to get to know what's happening at the microphysics level, at a micro level. Okay, so we will look at the warm rain process, ice rain process, and the implications on rainfall. So here are the results. Now, first of all, in the first experiment, where we changed the vertical structures of theta and RH, we get the following environment. So these plots show, firstly, the specific humidity, which tells us the moisture content per kilogram of air. Okay, and on the second plot, it shows us the scene or CAPE, convective inhibition or CAPE. How likely is convection going to happen? If it's negative, then convection is very unlikely to happen. If it's positive, then convection is likely to happen, and the degree of its likelihood will depend on the values. Now, the third plot is the vertical velocity, which is the upward movement of air from the ground up. Okay. Now, in this plot, the altered environment is represented by the golden line, and then the past environment is represented by the blue line. Okay. So what do we see here? We see in the altered environment an increased moisture in the boundary layer here. In the boundary layer here, okay, compared to the past. And then in terms of CAPE, we also see a larger CAPE in the boundary layer for the altered, and less CAPE for the altered in the middle layer. Now, for the upward motion of air, we see that the altered environment is consistently weaker than the past. So given this kind of environment, what type of clouds would form? Okay, so this gray line represents the ground, and here are the clouds. The blue one for the past cloud, the golden one for the altered cloud. Okay, so we first look from the bottom up. The cloud base height, where do they form? So altered cloud actually form at a lower height, okay, about 188 lower. The freezing level is higher in the altered cloud, and then the cloud top height is lower in the altered cloud. So that gives us a deeper warm cloud layer. Okay, here it's deeper compared to the past, and then a shallower cold cloud layer compared to the past cloud. All right. So now let's dive into the microphysics and see what's happening in these clouds. So the depth of the cloud layer is an indication of how active or not active the rain forming process is. So in this part, lower part, because it is shallow in the past, it is less active. So there would be less cloud water and rain. Whereas on this altered cloud, because it is deeper, so it is an indication of a more active warm rain process. So you would get more cloud water and rain. And then the same with ice processes. The deeper it is, the more active they are. The shallower it is, the less active they are. So this can be supported by some of these plots that I will show here. On this first plot, you see it is the rain mixing ratio, so the amount of rain being produced. So we see that the altered environment actually produced more than the past environment because of the depth. Okay, it is deeper. All right. And if you notice there is a dip in the rain production in the past, that's because in the past cloud, instead of it forming rain, the water is actually being lofted up into this cold layer of the cloud. So more ice is formed in the past cloud instead. So what is the implication on the rain? So here's the plot to show that. On the left y-axis, it shows the rain rate, so intensity of rainfall. And on the right y-axis, it shows the accumulated surface rainfall. And we see again that the altered environment has more intense rain initially. And then the rain fall out so quickly, I mean, all of it fall out at once, that less gets into the ice phase. Less gets into the upper part of the clouds. So that is why, you get less active ice processes. And then in terms of surface rainfall, the altered environment actually accumulate less surface rainfall compared to the past cloud. Again, because most of the rain has been rained out. So there is less water available for more growth in the cloud. Okay, so that explains why. So we move on to the second experiment. Again, the same. In this second experiment, we change only the vertical structures of theta. Okay, and the altered environment is represented by the green line. So we see that there is less moisture in the boundary layer, but more in the middle layer. And then we see actually more thin with less cape compared to the past. And then very obvious weaker updraft compared to the past. So this can tell us, you can make a good guess that this will be a very weak convection. And it is actually quite weak. Okay, so again, we look at the cloud structure, lower cloud base height, higher freezing level, lower cloud top height. Pretty similar to the first experiment, right? And even the depth of the warm cloud layer is deeper in the altered cloud and then shallower in the cold phase of the altered cloud. So pretty similar. However, their microphysics are different. Okay. So even though the altered cloud in experiment 2 has deeper warm phase cloud layer, which should have more active warm rain process. However, what we see is that the overall water content in this cloud is very, very low compared to the past cloud. Okay, that's because it has less moisture to begin with. All right. Now we also see that the ice processes in the altered cloud is almost non-existent because there is no green in here in the altered cloud. So we can conclude that in this experiment too, the cloud actually don't reach up to the ice processes. It's very, very weak. Okay. Now experiment 3, where we change the vertical structures of relative humidity, we get the following environment. Okay, the altered environment is in the purple line. All right, we see everything increases. So opposite to experiment 2, we see a more stronger convection in experiment 3. And I think you would also guess it right that we get a bigger cloud in this experiment. Okay, but one thing's for sure, the cloud base in the altered cloud is always lower. Okay, and in this case, the freezing level stays the same. There is no difference. And the cloud top height, definitely it is higher in the altered cloud. Okay, so what do we get? We get a deeper warm phase and we get a deeper cold phase in the altered cloud. Okay, so I think you would also make a very intelligent guess here that there will be a very strong warm rain process as well as very strong ice rain process. Okay, which you are right. All right. Now, if we look at the plots here, look at the rain mixing ratio. I do have to apologize here. I just noticed this last minute, at the last minute, that the lines are in the wrong colors. So this one, the blue line is actually altered, and then the purple line is actually the past. So we see that in the altered part, rain is being produced very, very rapidly or a lot, okay, due to these more active warm rain as well as more active ice processes, okay. And when we look at the ice particles, ice, snow, and hail inside the cloud, we also see that the altered environment has more of them due to the deeper depth and more active ice processes here. So let's try and see, in terms of rainfall, what implications would this have? Not much difference, right? Okay, now in this plot, the lines are correct, all right? So what we see is that initially we see a more intense rain for the past, whereas in the future, the rain is actually quite steady, okay? But in terms of accumulated rain, the altered cloud actually accumulated more rain, even though it is, pretty similar. But this is only for this location in Jasper. In all other locations, they actually show a wide range of responses. But on average, this is the average result. Okay. So you can start to see already that these clouds start to behave very, very differently. And there's so many things to understand and to analyze. Okay. So we'll get to that in a couple more slides, okay? I'll just end with this experiment 4, where it's about the warming experiment, okay? So in this kind of environment, the altered environment has less moisture and less cape and less upward motion of air. So we would expect a weaker cloud, okay, as expected. But also as expected, we get a lower cloud base. Now this time, a lower freezing level, and then a lower cloud top height, which gives us more or less similar depth of warm phase, but very significantly shallow cold phase in the altered cloud. Okay, so if we look at the rain mixing ratio, we see that even though this cloud is quite small, but they have pretty similar activity of warm rain process. However, the altered cloud actually produce more rain, okay? And when it starts to produce more rain, as soon as it starts to produce, it actually falls out very, very quickly, okay? It falls out very quickly, and then therefore it remains lower than the past. but the accumulated rain, it remains higher than the, sorry, not the past, but the original environment. Now, an explanation I can give to you as to why this original environment accumulated less rainfall, even though it's a big cloud, is because of its stronger updraft, stronger upward motion. So it gives buoyancy to the air in the cloud to stay up above the cloud, up in the air instead of going down. Okay, so that's one of the reasons why this original environment has accumulated less rain than the altered smaller cloud. So here's the summary of the experiments. We have looked at the perturbations and what happens to the thermodynamic environment. And we have also looked at how the physical structure of clouds changes. And finally, we looked inside the cloud as to how the microphysics are changing. What I'd like to bring to your attention is this. In all of the experiments, clouds form at a lower height, okay, compared to the original environment. And then the next thing is we see a very active, if not, very active warm rain process across all experiment. Okay. Another thing that I'd like to bring to your attention is that in all experiment but experiment 2, so experiment 1, 3, and 4, they produce very intense rainfall, okay? But experiment 2, very weak cloud, so less rain. So that tells us that if we change the vertical structure of theta, of the temperature, it can actually weaken the cloud, okay? So, yeah, and I would like to conclude by giving you a take-home message, several take-home messages, that with a change in theta, in temperature with no warming, it will reduce the cloud size and cloud water content. If we change the relative humidity with no warming, it will increase the cloud size and cloud water content. Now, if we have both changes of the vertical structure and with warming, okay, the effects actually cancel out and the overall cloud development is actually pretty weak, but it can still produce very intense rain, okay? So that brings to this last conclusion that in all of these cases, warm rain process is shown to be sensitive to the changes in thermodynamic environments. So in a warmer world, or even in any kinds of climate change, we would expect warm rain process to play a more dominant role in forming our rain. And therefore, we would get rain very quickly and very intensely. And that would give, that is a threat, really, as for flash flooding, okay? Now, as with all research, there are some caveats, okay, disclaimer. The results presented here may be too general because I'd like to cater to a wider audience, but the gist remains that the results may not be representative or robust due to the use of only one type of global climate model. Okay, it is most ideal to use an ensemble, a group of climate models rather than just one. Okay, but it is evident that climate change affects cloud development. Okay, as you have already seen, so many different responses. Okay, and in particular, it is the changes in thermodynamic structures that have shown to significantly affect cloud development. And the only thing is that thermodynamic structure, not many people, it's not widely studied. So it needs to be taken into account in future climate impact research. So that is all for my presentation. I hope I presented on time. Thank you very much for your attention.
Thank you very much, Dr. Marieanne, for your wonderful sharing about the formation of clouds, cloud structure, and the thermodynamics behind the cloud formations and different type of cloud structures. So we hope whenever we will saw the clouds, your talk
my pleasure.
Will be it will be remind your talk. Thank you very much, Dr. Marieanne. So we will take all the
Yeah, I hope
question
so.
at the
Yeah.
at the end of both talk. Huh? Okay, so now I like to invite our
Okay.
invited speaker, Dr. Sara Qureshi. So Dr. Sara Qureshi is the Chief Executive Officer and co-founder of Aero Engine Craft Private Limited. This is the first Pakistan commercial engine and aircraft research and development company that is developing environmentally safe, constant-free aircraft engine for the global aviation industry. Dr. Sara has a PhD degree in Aerospace Engineering from Cranfield University, United Kingdom. Her area of specialization is aerospace propulsion, whereby she worked on the development of Contrail-free aero engine that was derived from a patented technology. During her PhD research, Dr. Sara assisted the inventor with patenting the Contrail-free aero engine. The invention has been granted two international patents and has a tremendous potential in bringing about an environmental revolution in the context of aviation. Dr. Sara converted this patent technology into a full-scale application ready to be used by modern civil transport aircraft. Dr. Sara has also recently co-invented and patented a supersonic commercial aircraft engine. She was awarded the Distinguished Aerospace Alumni Award by Cranfield University in 2020 for her leadership role and dynamic professional contribution to her field. In addition, Dr. Sara also served as a visiting academic at the School of Aerospace at Cranfield University, United Kingdom, where she provides technical feedback on research on environmentally safe aircraft engine. Dr. Sara is also a prominent voice on sustainable aviation in the media. She is considered to be a trailblazer for women in STEM and inspiration for women leaders in aerospace around the globe. She is an also expert at the Solar Impulse Foundation, where she evaluates green solutions for the world as an active member of the World Alliance for Efficient Solution. So now I will to invite Dr. Sara for her talk. Dr. Sara, now the floor is yours.
Bismillahirrahmanirrahim. Assalamu alaikum. Thank you very much for this introduction, and thank you, Dr. May, for your very enlightening presentation on clouds. I think I took away a lot of learnings from here. Okay, so we have a there is a connection between clouds and the aviation industry, and that connection is basically because the aviation industry produces artificial clouds called contrails. So contrails is basically the byproduct, the combustion byproduct of the fuel burn in an aircraft engine is water vapor and carbon dioxide. Now, when this water vapor leaves the hot exhaust of an aircraft engine, it converts into an artificial cloud. It's not a natural cloud, but it's an artificial cloud, which is also known as a contrail or condensation trail. So it is called. It also then, when it stays in the atmosphere for a long time, it forms persistent artificial induced cirrus clouds in the atmosphere. So now I would take you to my presentation and talk about the impact of contrails. Okay, can you see my screen now?
Yes, we can see.
Okay, and can you hear me well?
Yes, clearly.
All right. Okay. So we are going to talk about contrail-free aero engines. But first of all, I would like to tell you that why are contrails so important, and what are their implications. So we have this is basically an introduction. We have designed a technology that is an add-on to an existing engine, so that you see these three engines are giving out contrails, and this engine, which has this add-on technology, is giving out a clean exhaust. So contrails are basically aviation's biggest environmental challenge at the moment, because they have a global warming potential, which is 15 to 20% of aviation-induced global warming, in the sense that carbon dioxide contributes, 3 to 4% to aviation-induced global warming, whereas contrails have a global warming potential which is 5 times more than that of carbon dioxide. So they contribute by 15 to 20%. And they form like an artificial blanket cover on the surface of the earth. So according to a report by Intergovernment Panel on Climate Change, 0.2% of our surface is covered with these artificial clouds at the moment, and this is likely to go up to 0.5% by 2050. So this, in this figure, you can see with the airplane is giving out these white clouds. So they're artificial clouds, obviously, and this is once these clouds settle down or neutralize, they form these persistent induced cirrus clouds. So as I said that the source of this cloud is the hot exhaust emissions, hydrocarbon fuel burn that contains water vapor as a combustion byproduct. And because it is released in the atmosphere, you are cruising at around 10,000 meters. So this cloud or this water vapor, when it enters the cold atmosphere, within the engine, it is like steam. But when it leaves the engine, it just freezes, because you are at a quarter bar pressure and 218 Kelvin temperature. So this freezes into an artificial cloud. So this is one of the references that I give, because a lot of people, when I talk about contrails, they say that it can, it is just water vapor, and it can, convert into rainfall. And I'm sure Dr. May will be able to explain you in more detail that every cloud cannot create rainfall, as we have also seen in her presentation. So basically what happens is that you see just a basic understanding that this is at 2000 meter, this is where your weather cycle operates according to this figure. Dr. May can correct me if I'm wrong. And we are flying at 10,000 meters. We are flying above everything else. We are even above the Mount Everest here. So whatever artificial clouds that form here cannot create rainfall directly. And so what happens is that they just form an artificial cover on the surface of the earth, and which is causing global warming. Now the challenges that we are facing with this kind of issue is that it is a very industry specific problem. Like on the ground, when you burn hydrocarbon fuel, you also get water vapor and you get carbon dioxide. But what happens is that because you are at 1 atmosphere pressure, sometimes, as we have seen in the presentation before this, that it just rises up, and there's this phenomenon of relative humidity and convection, and rainfall occurs. But when this water vapor is released at 10,000 meters, it does not cause rainfall. It is just a cloud. So this is a problem specific to the aviation industry. And with carbon dioxide, a wide spectrum of industries are involved. It's happening in the air, but it's also happening on the ground. So there's a lot of widespread knowledge, widespread awareness, and there are ways to mitigate it as well. And people have auxiliary systems. There are plants, emission processing plants with factories, and there are so many solutions. But with aviation, we have to work under very tight constraints. Number one, we have because it's industry specific knowledge, it is people are not aware of the contrail problem. Secondly, it's not visible. It's happening in the sky, we can't see it, so we don't react to it. Thirdly, you can't grow. There are no offsets. You cannot grow trees in the sky to clean the air or to balance the temperatures. And you cannot also have auxiliary systems. Whatever technology should be there has to be on the engine and on the aircraft to mitigate contrails or mitigate global warming and climate change. So in that respect, the aviation industry is working on different technologies to bring about this change, and one of them is to work on contrails. To me, this problem on contrail suppression was given as a research question during my PhD, and we studied. There's a lot of research on contrails, but so far. And there have been some technologies that have been developed, but people are not really taking those technologies to a commercial level, to a product level. So with the technology that we invented, this was invented as a core idea by my father, with whom I worked during my PhD as well, and the technology was patented. And then I developed the engineering model of this technology and the turbo machinery, which is an addition to the jet engine. And so that it is fitted at the end of the engine so that it can process the exhaust emissions and extract the water vapor content of the emissions, convert it into liquid water, and store it on the aircraft. So we are basically addressing these sustainable development goals through this company. The company has been set up to convert this technology into a full-scale commercial product. And with this, we are trying to reduce aviation-induced global warming. And since water is created in the process, it can also contribute to the problem of water scarcity. And it has been modeled as a circular economy, just to get revenue for the engine manufacturers as well as for the airlines, because the airlines can opt for emission trading, contrail emission trading, and also for artificial rainfall. So with our invention, the first thing we are doing is, because earlier there are lots of technologies, when they talk about contrails, the work on contrails started during World War II, because enemies could detect planes because of this white cloud behind the planes. So, but they were using chemicals to disperse contrails, and now there are different ways to disperse them, to mitigate them by flying lower, flying higher, or heating up the contrail so that it forms smaller particles. But our focus is to eliminate the source of contrails so that water vapor is not introduced in the atmosphere. Number one, because even if it does not manifest itself as a contrail, it is still introduced into the atmosphere as a greenhouse gas, because it has a size which contributes to it's in the form of a gaseous and a vapor that contributes to global warming. Secondly, we're trying to create and store water within an aircraft. This is the first attempt to create water from an aircraft engine and then to store it on the aircraft, and using fuel emissions as a resource to generate artificial rainfall. Okay, so these are just some patterns, and you see we are seeing these just to explain contrails, and these are basically how we started this work. So this was, as I said, part of my PhD question, and then the concept was validated, the engineering model was formed, the patent was filed, and then the PhD was awarded on this, and it also won an award for clean technologies. And the patent was granted in 2017, when we and in 2018 we launched this company, Aero Engine Craft, to develop this technology as a commercial product with some seed funding. And right now we are into our advanced product and ecosystem development. The core product development has completed, and now it is in the testing phase. And we are a bit behind schedule because of this disturbance due to the COVID. Okay. So you see, for any technology that has to get airborne, we have a standard NASA's technology readiness level. One is like just TRL. One is like a basic idea, and two is like some formulation of the design, and then we have simulations and mathematical modeling. So in a PhD research, you go up to TRL3 or TRL4. And then when you prototype the technology and you make a model out of it and you test that model, so you keep going up where you're testing in an environment. So we currently are approaching TRL6, that we have tested we are testing our technology on the ground. Component testing is complete, and the whole integrated technology is being tested right now. And so you keep moving up, you test it in space, in the air, airborne testing, and you have certification. And then TRL9 is when you actually commercially launch a technology. So this is just the basically in a company breakdown is usually that you need to invest it's very high precision technology, so you need to invest like 40% of your budget into equipment and materials, the remaining 40% into human resource, and 20% into overheads. Now, talking about the market for this technology, where you have a turbo machinery that is going to, process the exhaust emissions of an aircraft engine. So the primary market is the engine manufacturers. It is a very monopolized market. We only have three major engine manufacturers who are producing commercial transport engines, which is Rolls-Royce, GE Aviation, and Pratt and Whitney. And then so they would be approached to incorporate this technology into the engine. And the secondary market is the aircraft manufacturers, because for the storage of water you need to there's some storage mechanism that has to go on the aircraft as well. And the environmental agencies are stakeholders, because they have to be compelled to pass legislation and define targets to reduce aviation-induced global warming. So this is our circular economy model, where we say that we are developing this Contrail-free aero engine here, which is going to provide a backup or an alternate to environmental agencies and regulatory bodies to pass regulations, because for regulations on emissions to come through, we always need an alternate technology. And the engine product is going to go into the engine manufacturer, the airframe product to the aircraft manufacturers, and they are going to integrate it to sell it to the airline. The airline can generate revenue by selling rainfall to local governments, and by achieving global warming reduction and getting Contrail credits. Okay, so currently we are seeking an immediate investment of $1 million to take this product further, because so far we have developed the prototype of the product, and we need to now make it on a full scale. So the revenue model is basically based on, when we license out our technology, and the patent to a manufacturer, and they usually give you like 3% of revenue um, as a standard industry benchmark. So so this is basically the concept. The research definition is that you condense and contain the water vapor content of exhaust emissions within the engine to prevent contrail formation in the atmosphere during flight. So and obviously the research strategy has it's like a very multidisciplinary topic, and that is also where my interest on clouds started, because we have to study the formation of contrails in terms of its water physics and atmospheric science, and then we have some condensation mechanisms for water vapor, and then the turbo machinery design, and then also the thermochemistry, because there are three gases in a combustion when the hydrocarbon fuel is burned, because you are combusting it with air. So air contains oxygen as well as nitrogen. So in the combustion gas, you get carbon dioxide, you get water, and you also get nitrogen and some parts per million oxides of nitrogen, which are another pollutant. So when we talk about the formation of contrails, it is governed by the Kelvin equation, and these are the different factors that basically determine whether contrails will be formed or not formed. So our conclusions and our studies have shown us that when the formation of contrail is actually the size of the water molecule or the water particle that is formed. When that is the emission is released in the atmosphere, and that size is basically dependent on ambient temperature, ambient pressure, and the saturated vapor pressure of water at that altitude. So generally contrails are a high altitude phenomena, for planes. So this is applicable to planes who number one fly at high altitudes like 10,000 meters, and these are long haul flights, 8-hour flights that fly at that altitude. And secondly, these, because they're flying for a longer time, so there's a longer amount of time where fuel is burned and contrails are released. So if we look at just a basic of atmospheric physics in terms of our altitude up to 11,000 meters from sea level, and how our temperature varies. So generally we are at 10,000 to 23 Kelvin, and this is our this is the ambient pressure. This is 26 kilopascal, or almost quarter of an atmosphere. And this is, we can see that the saturated vapor pressure of water is very low. So that means that that water is going to condense at that altitude. And the particle radius, again from the Kelvin equation, we can see is 0.7 microns. So now for this, we say that when the particle radius is very small, in the order of 0.01 microns, it forms a cloud condensation nuclei for other clouds and vapor particles to coalesce on it. And in the order of 10 microns, it's just a water vapor or a cloud. And if it's 100 microns, it is a raindrop. So our target is basically to condense it to a bigger particle size, so that it does not form a cloud, but rather forms a raindrop. Okay, and then we have also looked at some actual values in the engine exhaust. So here we see this is the high power turbine and low intermediate turbine, low power turbine, nozzle, and bypass. So this is how the temperatures are varying in these in these regions of the engine. And this is again because this is just after combustion. You go up to 1600, 1800 Kelvin. And when we are coming down, in the nozzle we have 663 Kelvin. So we can see from here that if we look at the particle radius based on the Kelvin equation, we are getting a negative particle radius, which means that the moment that water particle is formed, it again evaporates into a vapor. So there is no water particle formed. In the bypass, you can see that the order is like that of a natural cloud because there is no hot gas. The bypass is just adding some compression to the intake air from the atmosphere. So contrail prevention is basically, there are two methods, distinct methods. One is contrail dispersal into vapor, that you make the particle size even smaller so that it does not appear as a cloud, but it just disperses and it is not visible. The second is to coalesce all the water vapor particles into water, which is contrail nucleation. So our process is basically focused on contrail nucleation. So there are different techniques for contrail avoidance, and there have been chemical additives, but that is just to hide the contrails for the military purposes, and it is not environment friendly. Then we have heat exchanger methods, but with heat exchange, for conventional heat exchangers, we need, because they're not very lightweight, so we need very lightweight technology to take up on the plane, and you need a heat exchanger which is the size of the engine itself. Then you have microwave excitation, that you excite, you provide some microwave radiation to the water vapor so that it disperses, it heats up and disperses into smaller size particles. Artificial seeding is when you just like we create artificial rain, that you allow some like we use silver iodide or whatever you allow, or even ice crystals are used to seed a cloud into ice, basically. And then ultrasonic is again giving some energy to disperse the cloud. Trajectory of optimization is like they have a criteria where they can detect whether contrails will be formed or not formed. That's called the Schmidt-Appelman criteria, based on again the different parameters that we discussed earlier. So in that case, there are studies which suggest that if there is no contrail, you can pass through regions where contrails would not be formed. Like you fly lower down, or you fly higher, or you fly by night, or you fly by day. They're varying the temperature and the ambient pressure. So this was the way we worked this out, was that we first had some baseline studies of an engine and its performance analysis before this device. So this we can see that the condensation device is fitted between the low power turbine and the core nozzle in an engine. So these are two different schematics of an intercooled recuperated engine and a standard turbofan engine. And then we also looked at heat exchange analysis, but as I mentioned, that you need the size of an engine itself, the heat exchanger, to condense all the water, because water vapor is just 2% of the mass flow, but you will have to really cool the entire mass flow to condense it. And also using a compressor as a condensation device, but that is not successful either, because when you compress through a compressor, heat is generated, and that does not let the gas to condense. So we had this pressure-based condensation model, the technology that we developed and patented. And so this is giving like a green exhaust concept, where we have first of all, this is a modular add-on attachment to the engine, so that you don't have to change the entire engine. And then it it eliminates the source of contrail, because it contains the water vapor within the engine and releases a cleaner exhaust. And because you're separating out that water, it is much easier to cool it further, because water is just 2% by mass flow of the engine. And then that water can be released at lower altitudes as artificial rain. And this technology can conform to environmental regulations on greenhouse emissions and contrail formation. And this is a very synergistic technology in the sense that it's also a turbo machinery. So any company or the manufacturers who are manufacturing engine components and turbo machineries, compressors and turbines already, can easily integrate it within their framework. It is not like a different, altogether different disruptive technology in that sense. And you don't need to redesign the engine. And this is going to be, inshallah, the first generation of contrail free aero engines, which would provide an environment friendly aircraft configuration and recover water as a net product. And this has become even more important because now there are trends that the aviation industry wants to switch to liquid hydrogen as a fuel instead of kerosene, because liquid hydrogen is a zero carbon technology. There is no carbon dioxide produced. But then again, although carbon dioxide is not produced, but water vapor is still produced, and the contrail coverage of liquid hydrogen powered aircraft would be 3 times more than that of an kerosene powered aircraft. So we can expect to see a white sky instead of a blue sky. So this is just the design philosophy of the the turbo machinery. And then we also have the thermochemistry of the combustion gases, because you see there are 3 gases, as I mentioned: carbon dioxide, nitrogen, and water vapor. Now when water vapor is condensing out, it is releasing its latent heat, and that has to be absorbed by the other 2 gases. And so we studied an intergaseous exchange of energy between these 3 gases, and it was validated that carbon dioxide and nitrogen act as a heat sink, and they absorb that energy, and some of that energy is absorbed by nitrogen, which is a favorable outcome, because you see, carbon dioxide and water vapor are both greenhouse gases. They both contribute to greenhouse effect, but nitrogen is not. So if it carries extra energy, that extra energy would not contribute to the greenhouse effect. So this is the basics of the design which were based on the vortex energy equation. And then we have the thermodynamic studies, the structural analysis, stator, rotor and blade design, shell design, and the mechanical modeling of the technology. And then this technology was tested on, an engine which is fitted with this technology was simulated, and then an aircraft which is carrying this new integrated part, in a way a new contrail free aero engine was also simulated to check whether the effect of the weight of the device and the changes in the length of the engine, how that would affect the performance of the aircraft. So the water vapor content in combustion gas is 2.5% by mass flow. And so as I mentioned, that if you separate this out, it is much easier, so that since it's not very a very high percentage of the mass flow, it does not give you a thrust penalty. And if you separate out this water, further cooling of this water is very easy. And then if you take a standard 3-spool turbofan engine, like for maybe the A380, it nearly consumes 1 kilogram per second of fuel. And the emission index of water for kerosene fuel is 1.25, which means that for every 1 kilogram of fuel burn, 1.25 kilogram of water vapor is produced. So in this case, we are getting 1.34 kilogram of water produced by a single standard 3-spool bypass turbofan engine during flight. So this equates to 160,000 kilograms or 160 tons of water produced during an 8-hour flight on a large body aircraft with 4 engines on board. So that is a lot of water. In terms of volume, fuel and water are equal because obviously water is heavier than fuel. So basically our research outcome was to prevent contrail formation, and then because of which the radiative forcing of artificial cloud covering the atmosphere is reduced, and the global warming due to the release of water vapor is also, and of contrails, is reduced. So and then we have, as I mentioned, that the heat transition to nitrogen, which is a non-polar gas and therefore does not contribute to global warming. So whatever energy that these gases are carrying, that is what they give out in the atmosphere, and which is given in a wavelength that contributes to global warming, right? So if you are giving it out, if it is absorbed by nitrogen and given out in the atmosphere, then it does not contribute to global warming. So as I said, that in our framework of research, we have a multidisciplinary approach. Then this is a new vision for the aviation industry and an environmental promise. And again, it's modeled as a circular economy to create value. So it has business potential. You have water recovery. You can start emission trading and global warming reduction. Okay, so as for the technology, it's named as an expeller, and that is developed from an patented invention into a prototype-ready engineering model, and it's also like an addition to the gas turbine family of components, another turbo machinery, and designed for airborne application. Because as I said, that it's very difficult to transpose some technology from the ground into the air, because you have to comply to airworthiness. The technology has to be lightweight and fail-safe. So some of the things that are, further research is going on, and for prototyping, we are looking at some practical issues. This is our team. This is myself and my father, some of our business consultants, and I have a visiting academic position at Cranfield University. So we have some academic collaboration. There are students who do research on the future elements of this technology. And then I was incubated at the incubation center for entrepreneurship, and we got some seed investment on equity sharing basis from Kanan, Pakistan, and then Pakistan Aeronautical Complex is supporting us with some technical resources. So this is my contact. This is our website and email, and these are some of the links. I will share them in the in the chat that you can use, and later. Thank you. This is myself and my daughter. So we can just now open up to questions.
Okay, thank you very much, Dr. Sara, for a wonderful sharing with us.
Video.
Okay.
The video first.
Okay, we can play the video. Please, technical team, please play the video.
Video number 1. So we can see these contrails are coming out of the engine. And And now with this device fitted, the contrail has disappeared because it has been processed inside. And then it is converted into liquid water. So when you are lower down in the atmosphere within the weather cycle, you can release it as rainfall. That's it. Thank you very much.
Thank you very much, Dr. Sara, for sharing us wonderful talk. And Dr. Sara mostly highlighted about the different technologies of aircraft engine which address the aviation-induced global warming in the atmosphere. So, Alhamdulillah, we finished both sessions. Now we are entering into our Q&A session. So, we have a few questions from our audience. So, the first question, this question to Dr. Marieanne from Dr. Firdaus. Dr. Marieanne, should I read or can you read yourself? Dr. Mary?
Unfortunately, I can't show. Yes, yes.
Okay.
So,
I will read the question from Dr. Firdaus. Is there any association between forested area and clouds formation? Is it important to conserve and rehabilitate forested area for water, sustenance, and flood mitigation?
yes, thank you for the question, Dr. Firdaus. Yes, there is an association between forested areas and cloud formation. In fact, that is actually my first PhD title. Well, one of the PhD projects that I was interested in University of Birmingham, but I didn't go with that project. So, you know, forests, they release a lot of pollens, okay, and not just pollens, but also volatile organic compounds. And these are aerosols, so they can, they can influence cloud formation because of these aerosols, okay? And then, yes, it is therefore very important to conserve and rehabilitate forested areas, not just to maintain the water cycle, but obviously to mitigate flood, because forests, the trees have very large roots that can hold the soil together. In fact, research on rehabilitating forests for the purpose of regenerating cloud is actually very active in Sweden, as well as in somewhere in South America. I'd like to say Brazil, but I am not sure. But definitely in Sweden, yes. So yes, there is an association between forested area and cloud formation. Thank you for the question.
Thanks, Dr. Mary. The next question is from Dr. Marina Mohammad. I'm sure you have definitely used statistical method in your cloud study. What kind of statistical method that is commonly used, and what statistical method that you hope to use and explore for your future studies on clouds? This is a question from Dr. Marina.
Okay, thank you so much for the question, Dr. Marina. Actually, I did not use any statistical method in my project because it is more of a process-based understanding. So I would really like to use statistical analysis to, sort of get some confirmation on the results that I get from this modeling simulation. I'm not really good at statistics, but I think what I want to use in the future is a type of regression analysis. I know that there are many advanced machine learning equations which can, like yourself, you do the penalized regression method where you eliminate factors that do not contribute to the response variable. So that's one of the statistical tests that I would like to use in my future studies on clouds. And it is actually in my plan to continue this PhD work in terms of the statistics side of it. So I would definitely like to collaborate with you on that. Thank you, Dr. Marina.
Thank you very much, Dr. Mary and Dr. Marina, for the question. So we move to another question. This question also for Dr. Marieanne. Question from Dr. Hee Ling Wong. Could you extend your experimental findings based on the current climate in Malaysia and what you do see might happen in the future?
Thank you, Dr. Wong, for the question. Yes, this experiment design, I would say, can be implemented in Malaysia using our current climate. I actually did write a research grant on it, but unfortunately did not successfully get the grant. But also, one of my grant collaborator, his team has developed a very high resolution climate data for Malaysian region. So definitely in the future, I would look forward to use this high resolution data and see how the clouds will change in different climate change scenario for Malaysia, so that we can plan our infrastructure as well as our water management. Yes, so thank you for the question.
Thank you very much, Dr. Marieanne. So the next question is an open question. This question from Mr. Mohammad Roslan. He's asking, can rainfall without clouds? If can, how it occur? I'm very curious to know this answer. This is the open question.
Yes, thank you so much for the question, Mohammad. It is a very interesting question. And yes, rain can fall without cloud. Now, how do they do that? Well, there are two ways actually. So one is without cloud. Well, actually, you still need the clouds, only that you don't see the clouds. Okay, so in locations where you don't see clouds, but suddenly you get rain, then it's possible that the rain from the cloud actually was blown away by very strong upper winds from clouds in another location. So that strong wind blows cloud in the other location to your location where there is no clouds, and that's why you feel like drops of water falling on you. But when you see up, there is no clouds. Now, another possibility where rain can fall without cloud is when the cloud is almost dissipating. So when cloud is almost dissipating, the cloud is actually very thin and translucent. You can't really see it in the, up very high up in the atmosphere. So when cloud is dissipating, it is actually indicating that the temperature is warmer. So when the temperature warms, the cloud can no longer stay in that liquid, ice particle very high up in the atmosphere. So they would just fall down. And as they fall, they encounter even warmer temperature, the ice will melt, and then you get rain. Although when you look above you, you don't see the clouds, because these clouds are very high up in the atmosphere and they are composed of ice. Only when they fall down that they melt and you get rain, right? So I hope that answers your question.
Thank you, Dr. Mary. And Dr. Sara, want to highlight
I would
something
also,
on this question?
Well, I'm not an expert on clouds as such, but as I said, my interest on cloud grew because we get artificial clouds from airplanes. So you see, a cloud, rainfall is water vapor. You always need the vapor content. As Dr. May said, that maybe the cloud is not visible, but the water vapor has to be there. Like even when they induce artificial rainfall, what they do is that there is the moisture is available in the atmosphere, but it is not condensing into rainfall. So what they do is that they go up in a plane and they spray silver iodide. Now silver has some affinity with water. Silver usually it kind of attracts water to itself. And we also do these coatings. If you want to condense water, we in machinery also we coat it with with silver. So that silver lining basically allows the small vapors to coalesce and to come together onto that silver iodide in the form that it becomes a larger particle that is actually raindrop. As I mentioned in my presentation as well, that it is actually cloud and raindrop or a cloud condensation liquid is the same chemical species, but it's just the size of the particle. That when it is very very small, when it's a molecule, it's just a water vapor gas. If it's in the molecular form, when it's in a few microns, it's a cloud. When it is a few hundred microns, it is liquid rain. So we can have, I think, rainfall without clouds, but we cannot have rainfall without water vapor content or moisture, unless that we have some artificial way of creating moisture, which is what we suggest in our technology with using the emission byproduct of fuel burn.
Thank you
Yes,
very much,
agreed.
Dr. Sara.
The essential thing being here, the water vapor and moisture.
Yes, moisture.
Okay, thank you very much, Dr. Sara and Dr. May for the answer for this question. So the next question we have from Mr. Hanafi Azami. This question for Dr. Sara. I am Dr. Hanafi from IIUM. My research is on alternative fuels used in aero gas turbine engine. How do you see the impact of biofuels and hydrogen fuels towards the formation of contrails?
Okay, as far as I haven't done a study on biofuels, but from what I know is that you know biofuels, as they say, are from biomass or whatever, will not never be enough in quantity to cater to the needs of the aviation industry. So now they are going into SAF, which is synthetic aviation fuels or sustainable aviation fuels, and making green kerosene or synthetic kerosene that would not, you know, uh, create emissions to that extent. But I still have to study on it. So that is my. As far as hydrogen fuel is concerned, now hydrogen is like is a very disruptive technology, and it has two elements. One is like hydrogen fuel cells, and the other is liquid hydrogen. So when you talk about hydrogen fuel cells, and which are is like kind of you can call it a battery or whatever. It's an electricity generating mechanism. But for that, the technology to date is not that advanced to be used for large aircraft for long haul flights. It can only be used on small planes for short haul flights, and it is a zero emission technology in the sense that hydrogen fuel cells don't produce carbon dioxide. They produce water vapor, but in a very low quantity, and that water vapor is not released out of an exhaust. It is just like when the fuel cell is working and generating electricity, that water vapor is formed and it is just stored. So that way it is called a zero emission technology, but it can only be used on a small scale for regional short haul flying. Talking about long haul flights for large aircraft, they are trying to, number one, use liquid hydrogen as a fuel. So with liquid hydrogen, number one is liquid hydrogen. It has its own challenges. One of the challenges that it is a very very disruptive technology. It's not just we would need to change the way airports are operating, the way, because hydrogen is a gas, and in order to take it aboard on a plane, you have to liquefy it. And to liquefy it, the standard traditional methods of liquefying hydrogen, or the conventional chemical processes that are well known, are basically, cryogenic cooling to 20K. 20K, is nearly sub-zero, 20 Kelvin temperature. So you really have to, liquefy it and then carry it aboard. So as much as I know for now is that, liquefying hydrogen on such a large scale is very, very expensive. It's like everything is possible, but when the scale also matters. It's like you say that we can make diamonds from coals. Yes, it is possible to make diamonds from coals, but it's a very expensive process. It's not a very practical process. Or making gold from radioactivity, again, you see. So the scale matters. So that's something. So this is like a very recent technology. People have really started working on this. That is one thing. And then hydrogen will make 3 times more. It will not make carbon dioxide, but it will make 3 times more water. Now, what they are trying to do with liquid hydrogen is that they are trying to get into hybrid propulsion with kerosene and with liquid hydrogen. Hybrid propulsion is that you have one gas turbine that runs on kerosene or hydrogen, and that in turn runs a series of electric generators. So you have a series of electric fans. Maybe you have seen some picture with, like, the wing has, like, instead of having one or two engines or one or two big propellers, it has like a line of small propellers. So this is called hybrid propulsion or distributed propulsion. And in this, one of the other research ideas that people are trying to work on is creating some synergy between cryogenic cooling of hydrogen and also of using superconductivity. Because if you are going as low as 20 Kelvin, then maybe it is because superconductivity for efficient use of electric energy is a very low temperature phenomena, and people have been trying to use it for various, that we haven't had a breakthrough in superconductivity, but they say that if we do, then we won't have weight constraints. So it would be like a breakthrough in aviation and in electric planes. But they are trying to synergize it with hydrogen at present and use that low cooling phenomena. The third alternate fuel that has been proposed is ammonia. Now, again, with ammonia fuel consumption, it was announced by one of the manufacturers' reaction engines, is that ammonia can creates hydrogen with a standard Haber process. So it's like essentially you are burning hydrogen, but instead of taking hydrogen aboard, you take ammonia, so you don't have to go through the process of liquefying hydrogen or cryogenic cooling, but you take ammonia. Ammonia creates hydrogen by the Haber process, and then in turn you use that hydrogen for it. I've written a very detailed article on this and on different technologies. Maybe I would share some links with you here so you can have a look.
Okay, thank you very much, Dr. Sara and Dr. Hanafi. So now we can take one more question. This is the last question, I think. This question is from Dr. Amal Najiha. So Dr. Amal Najiha asking, in current pandemic era of COVID-19, what is your opinion on the future of aviation situation? Less travel via aviation could reduce climate change. It's a question from Dr. Amal Najiha to Dr.
Okay.
Sara.
Thank you for the question, Amal, and I also want to thank Dr. Amal for introducing me to this forum and inviting me for this talk. First of all, I would say that this less travel is a very short-lived phenomenon. If you extrapolate into the future, globally, we are now trying to go on to Mars. Okay, so for Mars, there is no option but to travel by air. There's no ground network, right? Because you see this trend with people they say that we are not going to fly, we're going to use the ground network because flying creates a lot of pollution. So Now, so the aviation will take off, and it has a lot of potential in the future. If you look at, you extrapolate it a few years from now. So the pandemic was short-lived, but the pandemic or the COVID-19 situation has in a way worked in the favor of aviation. Number one, what has happened is that the aviation industry suffered a loss during the pandemic, and the big governments were asked to bail out the aviation industry because of the loss it has suffered because of because flying stopped altogether. So the governments are now, they are bailing out the industry on the condition that the industry would support environment-friendly technologies and that they would introduce environment-friendly technologies. So there is an incentive, and by the government, not exactly an incentive. Yes, you can call it an incentive, and uh, uh, terms and conditions set for the aviation industry. So the industry has started to work in that direction. This is one advantage. Um, Secondly, because the other advantage is that because day-to-day operations were stopped or reduced, so the industry itself had more time to focus on the R&D on new technologies. Because you see, otherwise, airlines are always busy, and then the engine manufacturers are also very busy. They have a backlog of order for engines and for aircraft. So now, because that all slowed down, so they had more, the priority shifted to R&D, research and development of new technologies. Thirdly, because once flying is resumed, we know that first it would resume for regional flying and for short haul flying. Long haul flights would take off a little later. So the advantage with short haul flights or regional flights is that because you have smaller planes, smaller flying routes, it is always easier to test new technologies. So whatever new environmental technologies come into commercial use, there would be an opportunity, a convenient opportunity to test it for short haul flights. And once they qualify and are certified for airworthiness on short haul flights on smaller planes, then there would be then it would be easier to scale them up for larger airplanes for long haul flights. So these are all the advantages that we see with the COVID-19 situation in terms of aviation-induced global warming and environmental technologies of the future. Thank you.
Okay, thank you very much, Dr. Sara, for your opinion and suggestion. Inshallah, we hope this pandemic era will be end soon and we can travel back again to everywhere. So
Inshallah.
I would like to thanks to Dr. Sara and Dr. Mary for the wonderful and great sharing with us. So both our speakers mostly highlighted on the development and formation of clouds and structures of clouds, as well as the what are the new technologies uh, in engine of aircraft which can reduce the uh, global warming in our atmosphere. And I hope, inshallah, these all sharing with us, it will be very helpful for our nation development. So by this, I like to thanks again our speaker, Dr. Sara and Dr. Marieanne, as well as our all the viewers, those with us since 1.5 hours. So thank you very much. Stay safe all and take care everyone and be positive. Assalamu alaikum warahmatullahi wabarakatuh. Allah Hafiz. Assalamu alaikum. Bye bye.
Allah Hafiz. Allah Hafiz.
Thank you. Bye.